Hello everyone. Are you guys able to see the screen?
Yes,
Okay.
visible to
Okay.
me.
Should I wait for 5 minutes or should I go ahead?
So I think you can start, no? What about others?
Yes,
You
sir.
can
Yes.
start so it will be, can complete it
Yes, sir. Yes, sir.
first.
Okay. So welcome everyone to this class on natural and induced fractures in tight reservoirs. And this is a sub part of the broader subject related to shale geomechanics. Okay. So a little bit of discussion on shale geology. So you can see that shales are often deposited in low energy areas in the ocean floor or in quiet freshwater basins where fine sediments accumulate. Okay, so you can see in this picture, those areas are ideal for settling of clay and accumulation of organic matter. So you can see this is as the sea level is rising from one picture to the next, because lower part of the ocean is quiet. So the shale is being deposited on this lower part of the basin. Okay, if uh, this is mostly in calm waters. But if you increase the velocity of the water or the turbulence of the water, then there will be deposition of other types of lithologies, but not shale. Okay. So as Madam already discussed, that shale has low permeability, meaning oil and gas does not flow easily in the matrix. So the natural and induced fractures create some pathways for hydrocarbons within the shale reservoir to reach the wellbore. Okay. So shale permeability typically ranges between 0.00001 to 0.001 millidarcy. And as you can see the comparison of different types of lithologies. So even if you compare tight sandstones, so tight sandstones have about more than 1000 times permeability compared to the shale. And if you talk about the cap rocks, such as anhydrite and salt, their permeability is very close to that of shale, like the low permeability shales. Okay, this is why the natural fractures in the shale and the hydraulic fracturing is very important in shale production from shales. So before we discuss the natural fractures, let us discuss the little bit of the type of induced fractures that can come in the core. Like these are shale core cartoons because of handling of the shale core. Okay, so you cut the core and then you bring it up to the surface and then you store it in some repertoire. So what happens is that during that handling, the the shale can get fractured. Okay, the shale cores. So these are some of the cartoons of the induced fractures like cup fracture, saddle fracture, petal fractures, petal center line, scallop. So these are, I'm not showing you the actual ones, but some cartoons. Okay. And sometimes these fractures will occur without this center line. Can you see my cursor or no? Can you see the cursor? Yes. Okay. Okay. So sometimes these types of petal fractures will occur without the center line. Okay. And if the center line fracture occurs, then it's called the petal center line. So these are some of the pictures you can use to identify natural fractures from induced fractures in shale cores. Okay. So now we are done with the induced fractures. Let us discuss the natural fractures in shales. Okay. So these are the actual representation of the natural fractures obtained from shale cores. So the first one, you can see this is a opening mode, like mode 1 fracture. It is called a tensile fracture, and you can see some cement within those fractures, okay, within that fracture. And mode 1 means it has just the opening mode movement. It does not have any shearing type of movement. Okay. Next one is a low angle shear fracture. So this is slightly angled, and you can also call them like a small reverse fault. Okay, like a very small size reverse fault, you can call it. And again, if you open this fracture and look at the surface, then you will be able to recognize some of the patterns. For tensile fractures, the patterns are somewhat different from the shear fractures. Okay. Then you have high angle normal faults. So you can see this is angled here, but it has some angle. It's not vertical. Okay. So if the shale core is vertical, so this is angle. So you can call it like a high angle shear fracture. So this is a very small normal fault. You can also see horizontal fracture here. Then another type of low angle fractures you can see here. Then you have these bedding parallel fractures. So these are the shale beds. Okay. And then there is this bedding parallel fracture. So sometimes the bedding planes in shales are really weak. So because of these weak bedding planes, sometimes it becomes easy to create natural fractures along the bedding. So these are that. Then again, you have a low angle shear fracture here, like you can see the angle forming. Okay. And this is the surface you can see of a high angle shear fracture. So this one. Then we have some type of fractures which are called diagenetic shrinkage fractures. So these types of fractures are very important for shale production from shales. Okay. So what happens? These types of fractures can store a lot of hydrocarbons in the shale, and these can contribute to a lot of oil and gas production from the shales. So what happens is that when the shale beds are deposited, and then after some time, there is something called diagenesis, in which the shale loses some fluid from inside. Okay. So because of this fluid movement out of the shale, there is shrinkage of the shale matrix, and that shrinkage will cause some of these bedding parallel fractures. So these are not related to stresses like the tectonic stresses, but actually due to volume reduction in the shale. Okay. So these are called diagenetic shrinkage fractures. And finally, we can see a slip fracture here. So these are some types of natural fractures you see commonly in shales. So the main question is how to identify which fractures are natural, okay, and which fractures are induced. That is the main question. If you take a shale core and ask that question, which are the actual natural fractures and which are the induced fractures, then and the reason you would ask that question is that you would actually use these fractures to build your natural fracture model, in which you can do some hydraulic fracturing simulations. So create those natural fracture models. You do not want to put some induced fracture in your model. You want to only put the natural fractures. So that's why it's important to identify the difference between them. So the most easiest way to identify natural fracture from induced fracture is the presence of this cement. Okay. So you can see these fractures, this white stuff within the fracture, that is natural fracture cement. Okay. And these types of cements are deposited within the fractures, the natural fractures, while they were forming in the geologic time scale, or maybe after also they have formed. You can deposit cements can be deposited in this. Okay, but if you are talking about induced fracture that happened at the surface, you won't find any natural fractures in them. If you open up, it will be empty. So this is one of the main ways to identify, and you can see in this picture to the left bottom, like this is a natural cement on the fracture. And it's not necessary that the entire surface of the fracture will be covered with cement. Okay? Sometimes only part of that surface could be covered with this natural cement. So even then, you can call it a natural fracture. Plus, you can look at the shapes of these fractures from the cartoon that I showed you before. Some of the induced fractures will have this type of geometry, okay? While the natural fractures will have these types of geometries. Okay. So what you see on this right, natural fractures, this is called conjugate natural fracture. You can see one fracture is going this way and one is coming this way. So these are very small normal faults which have been filled with cement. You see this part of the fracture is not cemented. You can see there is a hole there, which is the uncemented portion of the fracture. While these fractures, they are random fractures. You see they are going in all directions. Like there is no pattern you can see on those natural fractures. So these are They have no direction, even though they are natural fractures. Okay, so they are mostly forming under localized stresses here. Well, these types of faults that you see are mostly influenced by the tectonic stresses. Okay, one thing about these fractures is that cement filling reduces the permeability of these natural fractures. So a natural fracture which has less cement is more permeable. A natural fracture which has more cement is less permeable for fluid flow. So the question is, what kind of natural fractures can form in these fractures? So, I mean, what kind of natural cement can be deposited in these fractures? So you can see the natural fractures, some of which are open like here and here. So if you take a thin section of these fractures and you put it under a microscope, you will observe different types of mineralogy of those cements. So the most common ones are the calcite ones, you can see. So this is calcite cement once you put under microscope. So within the microscope, there are two types of settings. One is the plane polarized light, another is the cross polarized light. Okay. So if you look at the cross polarized thin section, then you will see this type of color for calcite. You see, these are called twinning, calcite twins, like some going this way, some going that way. So this is the sign of calcite cement. Okay. And you can see the edges are not regular, they are rough edges, okay, for calcite crystals. Then another type of cement that you will observe. So this is a CaCO3, okay. This is called gypsum. This is another type of cement. And its formula is CaMgCO3 2. So you can see gypsum cement is very colorful, extremely colorful under cross-polarized light. And you can see the edges are quite smooth of the gypsum cement. So CaMgCO3 2. This is. Then another type of commonly observed cement is the quartz cement. So SiO2. Okay. So this is a thin section of quartz. You can see rough edges, irregular size grains, and then the colors are mostly black, white, or gray. So this is a quartz cement. And finally, so gypsum, okay, one thing. Sorry, gypsum formula I mentioned wrong. It's CaSO4 2H2O, okay? That is gypsum, CaSO4 2H2O. And dolomite formula that you see here, it is CaMgCO3 2. That is the dolomite. So if you talk about dolomite thin section, then it looks like rough skin, like rough dead skin under microscope. So CaSO4 2H2O, and this is CaMgCO3 2. Okay. So these are the four common types of cements that are deposited in these natural fractures. Open eyes, you cannot understand it, but once you put under microscope, or if you put HCl, like HCl acid on these, if it's a calcite cement, it will start fizzing. Okay. And among these, calcite cement is the most common one because calcite has low solubility. It's very high solubility. Okay, so it can dissolve from anywhere and it can get deposited at any place. So calcite has high solubility, and that cement is even the most common in quartz-rich rocks. And these are the natural fractures that you see here. One a very peculiar type of natural fracture is this. What you see here is this rough edge fracture. It's called stylolite, Stylolite, stylolite. Okay. So all other fractures like this one, these ones form under tension. Okay, so the rock is pulling apart a little bit, or the fluid pressure inside the rock is high, which is causing these natural fractures. But this one is purely compressional fracture. Okay, so two pieces of rock, if you push them very tight, if you keep pushing them extremely tight, then some of the grains will dissolve from the rock, and that forms these types of stylolites. So these are type 4 fractures called stylolite, while this one is a type 1 or 2 or 3. Okay, type 1 is mostly opening mode fracture, which is this one. Type 2 are like faults like this and this. And there is a type 3 which has Caesar type of movement, which I cannot show you here. But and this is type 4, okay, which is completely compressional fracture. Next, when we talk about natural fractures in the petroleum industry, we cannot forget image logs. Okay. So in many wells in the petroleum industry, image logs is acquired, so that the main advantage of image log is we can image the entire wellbore. Okay, while for core you cannot image the entire wellbore. You cannot have the entire wellbore cored, okay, because it's expensive to core the wellbore. While imaging the wellbore using image logs is relatively less expensive. So there are two ways in which you can display the image logs. One is this one, in which it is as if you are inside the wellbore and you are looking at the wellbore walls. Okay? So this is that image log. Another one is if you roll this image log, then it would look like a core. Okay, so this is the core view. It is as if you are looking at a core. Okay, both of them are the same thing, except you have displayed them in two different ways. So what do you observe in these image logs? So this one that you see here is what? And this one. So these are called the drilling induced tensile fractures. So while you are drilling the well, if the mud weight is even little bit high, okay, normally in most cases you will get these drilling induced tensile fractures. Okay, so these will form in your maximum horizontal stress direction. Okay, whatever is the direction of your maximum horizontal stress. So this is a vertical well. Okay, in a vertical well, you will see this drilling induced tensile fracture along the entire well bore. Okay, and these form in the maximum horizontal stress direction. So you can see this is called a Rose diagram, and you can see that these this is the direction of what? Induced fracture. Okay, so drilling induced tensile fracture. This is the direction of what? SH max, maximum horizontal stress direction, and the other direction 90 degree to that, you can have these breakouts. Okay, in the wellbore. So this is the direction of what? The minimum horizontal stress. So the Rose diagrams indicate the direction of the breakouts and drilling induced tensile fractures. Okay. So this is the simplest representation of this. Okay. So what do you think is the in this area? What is the direction of the SH max according to this figure? So this is east, this is north, this is south, and this is west. Okay. So the SH max direction is most likely about north of, so it's between northeast and east. So we can call it north-northeast. Okay. So this is east and this is northeast. The SH max is north-northeast in this case. Okay. And this is the pad which actually images these wellbore. So you can see these pads have what? Resistivity tools which rub. So these slide along the wellbore. And they take these so what are these colors? These colors are not actual photographs. Okay, so these are the actual rock properties. So some parts of the wellbore have different resistivities than the others. So these are actually resistivities magnitudes in different colors. Okay. You cannot just go and take a picture, even though we have those tools which can actually take a picture of the wellbore, but in this case we are just showing the properties of the wellbore as pictures. Okay, so you can image the resistivity, or you can image the sonic velocity of the wellbore. You can also image the density. Okay, so each layer of the rock will have different density. Okay, so using the density contrast, you can image the wellbore. Okay, so in this case it's a resistivity, and the reason we have these places like white patches here, like white. Okay, why is that? Because these pads are not touching each other, so there will be small distance between each of those pads, and those are the regions with no data, and that show up as white in these image logs. So these are the gaps. Okay, so please take a look at this image. What do you see there? So in this image, you can see some natural fractures in this image log. So these are the natural fractures. Okay, you can see them here. And the reason you are seeing these sinusoidal shapes of natural fractures is because you are projecting a cylindrical object onto a straight plane. So that's why you are looking at these sinusoids. Okay, Actually, these are straight planes that intersect the wellbore. One thing about image log interpretation is that the lower the resistivity, darker will be the color, and higher the resistivity, brighter will be the color. So if you talk about these natural fractures, do they have lower resistivity compared to the matrix or higher resistivity compared to the matrix? So as I mentioned, that lower resistivity is shown in dark color. Okay.
Lower.
Yeah, lower. Yeah. So why is this lower? Because these natural fractures are mostly not cemented. Okay, or maybe slightly cemented. So slightly cemented means what? You will have the some type of fluid in there, or some type of drilling induced. The drilling fluid or some type of natural fluid there. And fluids always have lower resistivity compared to the solids. Okay, so that's why you see these fractures have a lower resistivity and shown in dark color. And if you want to understand the direction of these fractures, so you can look at this representation. These are called tadpole plots, TADPOLE, tadpole plots. So in this case, if you look at these tadpole plots, the tails of those tadpoles indicate the direction of the dip of those fractures, in what direction they are dipping. Okay. So in this case, all of these natural fractures are dipping to what direction do you think this is? So if this is if here it's south, north, west, east, then what is this? It is southeast. Okay. So most of these natural fractures are dipping in the southeast direction. And if you talk about the magnitude of the dip, so you can see this scale. Okay, 0 degree means dipping 0 degree. 90 degree means what? Dipping 90 degree, which is a vertical fracture. Okay, 90 means vertical, 0 means what? Horizontal. This means these fractures are dipping at about what? About 80 degrees. Okay, towards the southeast direction. So where these tadpoles are located indicate the dip magnitude, and where these tadpoles are pointing show the dip direction. Okay. So again, if you look at these ones, these are most likely the bedding tadpoles representing the bedding. Okay. So you see the bed dips are really low. They are close to 0 degrees, maybe 5 degrees. The beds are dipping 5 degrees, almost horizontal. Okay. And the direction there, the beds are dipping is northeast. So you can see the tadpoles are pointing northeast.
Sir, how can I know the length of the fracture, like from the sand face?
Yeah, length of the fracture you cannot see in image logs. Only the orientation and dip and the dip direction. Okay. Length you cannot see because whatever is the length of your core or the wellbore, diameter, that's all you can see. Okay, not beyond that.
And sir, that will also depend upon the depth of investigation of that logging tool.
No, depth of investigation, we are looking at the wellbore. We are not looking beyond the wellbore. Okay. So in this case, we can only image the wellbore.
Okay.
Yeah, if you want to estimate the length, there are other methods. Even that will not give you exact length. Okay. But yeah, mostly if you want to look the fracture length, go to an outcrop and look at the fractures, like how long they are. Okay, that's the only way to actually look at a natural fracture length. Okay. So
okay,
yeah. So here you can see if you talk about the bedding. So in this image log, you can see the beds are dipping at about 45 degrees. Okay, and they are dipping in the southwest direction. Okay, so these are the beddings. Okay. So some beds have low resistivity, some beds have higher resistivity because they are brighter. So actually, when you have these tadpoles, there should be a legend telling whether it's a bed or fracture or whatnot. Okay. Look at this. This is an example of a closed natural fracture. Closed means what? Closed means it's completely cemented natural fracture. So you can see the natural fracture is whiter compared to the matrix. And this picture is the same zone, okay, except that they have used different types of imaging. Like they have imaged this zone a little bit differently, but it's actually the same zone. Okay, you can change your image settings in a zone, so you can get different colors. So in this case, the beddings are more clear in this one. Okay. In this case, the bedding is not that clear. But the natural fracture that we are focusing on, you can see it has a higher resistivity. which is indicated by which indicates that there is cement in this fracture, completely cemented. What do you think? Will it have a high permeability or low permeability, this natural fracture?
Low.
Yeah, low, because it's completely cemented. Okay. And what direction is it dipping, this fracture? You can see.
Southeasterly.
Yeah, you can see this low trough. Okay. It's dipping in approximately 240. Like if this is 180, this is 270, then this is around 240. Okay. 240 means what? Southwest, because 180 is south, 270 is west. Okay, so 240 is approximately southwest. So this fracture is dipping approximately southwest direction. Okay. So if this is a core and you try to retrieve a core, it's possible that the core would break along this natural fracture if the cement is not strong. Okay, and if it's strongly cemented, then it would not break there. So in this picture, we have imaged both closed and an open natural fracture. So this is a closed one. You can see high resistivity, low permeability, and this is an open natural fracture. Okay, which is has high permeability. Okay, as it's shown in dark color. So dark means high permeability. So they are conductive fluid pathways. So one easy way to remember is that electric conductivity is also hydraulically conductive. Electrically less conductive is also hydraulically less conductive. Okay. Now there is a drilling induced tensile fracture that I talked about before. What direction does it form? Do you remember? It forms in what? Go to this picture. Okay. It's forming in the SH max, the maximum horizontal stress direction. Okay. So this is a vertical well, and this is the direction of SH max. Okay. These drilling induced tensile fractures. And do you think the drilling induced tensile fracture should have low permeability or high permeability? It has low permeability, right? Because actually these fractures don't go too far from the wellbore. Unless you have extremely high mud weight, then it will fracture the entire wellbore, and these fractures will go far away from the wellbore. But under normal conditions, they will stop at less than 1 inch from the wellbore. Okay, so they don't go too far into the wellbore. So it's not very dangerous thing to happen. So yeah, because it's filled with drilling mud. So drilling mud has lower resistivity compared to the matrix. So that's why it looks dark. Okay. Okay. So look at this image log and tell me whether it's a natural fracture or whether it's a drilling induced tensile fracture. So these are actually drilling induced tensile fracture. Okay. Now you might ask why, because the DITF, drilling induced tensile fracture, looks like this. Okay. They go along the wellbore. Then why is it here that they are doing this pattern? Okay. This is called, by the way, N echelon pattern. ENECHELON, N echelon pattern. The reason is this: when drilling induced tensile fractures form in a vertical wellbore, then they will go from top to bottom. Okay. But if you are drilling a deviated wellbore or horizontal, then they will not be like a straight line. Okay, they will form these types of N echelon pattern. And the reason you can call it drilling induced tensile fracture and not natural fracture is because if it were a natural fracture, you will see the entire sinusoid here. Okay. Again, so what you see here is a repeated half sinusoids. Like this part there is no fracture. Again, this part there is fracture. So what happens is that this part of the wellbore is going into tension. Okay, so once it goes into tension, it fractures while drilling. This part of the wellbore and this part of the wellbore is what? It's under compression, so it's not fracturing. So the major difference between, I hope you understand, even though it looks like a natural fracture, it's not natural fracture because it's the entire trace of the fracture is not visible. And if your mud weight is too high, then what will happen? These fractures will propagate away from the wellbore, and then you will start losing the mud, and then finally you may have a wellbore blowout from another zone of high pressure. So now we are done with the natural and drilling induced tensile fracture. Now let's discuss the hydraulic fracturing that that madam was already discussing. So this is the same thing. What you do is you drill a vertical well and then you make it horizontal into the shale layer. So this is a Marcellus shale, and then you put the casing. Okay, after you put the casing, you perforate. You make your perforations, and then stage by stage, you what? You fracture the wellbore, and what you pump is a mix of what? The fracturing fluid plus propellant, which is you call it slurry. And before the slurry, you pump the pad stage, where you just pump the drilling fluid and not the fracturing fluid and not any propellant. Okay? So once you are done with this, the well starts producing oil and gas. Okay? 1 second. Excuse me. So these are some of the software you can use to simulate hydraulic fracturing. So you can see there are different softwares such as this DrillWorks Predict from Halliburton, Trackman from Golder. Then you have Gopher from Barry Associates, Petrol Reservoir Geomechanics, Baker Hughes Jewel 6, Flag 3D, and Elfen Rockfield. Okay. So this DrillWorks Predicts is a Halliburton software. It is a premier software in large oil and gas companies, and it can perform different types of analysis such as pore pressure, well planning, well placement, wellbore stability, caprock integrity, real-time wellbore stability, okay, reservoir compartmentalization, seismic velocity processing, leak-off analysis, all of that it can do. Okay. Next is the Frackman. So this is one of the best software if you want to model your natural fractures that you measured from your outcrops or from the core data. Okay. So you make your natural fractures, then you pump your fluid into this software, and then you get your extent of the hydraulic fractures. Okay. So geologically, this is the most realistic one. Then you have Gopher. Gopher is mostly being used by ONGC and other companies. It mostly deals with hydraulic fracturing and nothing else. Okay. It does a bit more than Frackman in terms of propellant displacement. Like in these fractures, you can model the propellant displacement, and you can do some history match of the fracturing pressure. You can also model like a leak of non-uniform solid and liquid velocity, propellant settling, all of those things you can measure here. Okay. One thing is this one. Okay, this software and all other software, they are continuum software. This means they do not model the natural fractures explicitly. Okay, implicitly they do some type of mathematical calculation to take into account the natural fracture effect, but they don't model them explicitly. But this one, it models, and this one, they model explicit natural fractures. You can actually put the natural fractures in the model. And Petrol Reservoir Geomechanics, it not only does hydraulic fracturing, but all types of geomechanical simulations such as wellbore stability and caprock integrity and whatnot. Then you have this Flag 3D and Elfen Rockfield. These are mostly used by the geotechnical engineers, even though they can model hydraulic fractures, but they are mostly not used by the petroleum industry, but the geotechnical industry, okay, like civil engineers, like miners and those people. And then Baker Hughes Jewel 6 is also a very commonly used software in the industry. And it can do all types of modeling, starting from hydraulic fracturing to wellbore stability. So this is an example of hydraulic fracturing. So let's say these are the natural fractures that you see here in blue. And then you drill the well. So you model the natural fracture first, then you drill the well, and then you pump your fluid. And you can see this is the stimulated reservoir volume because of hydraulic fracturing. and these are the places where your fracturing fluid went into. Okay, so this is the final model pore pressure. So obviously the pore pressure will increase after you fractured the well. Okay, and this is the fracture dilation, means how much the fractures are opening. So red areas here mean the fractures have dilated a lot, they have opened a lot. Okay, then this is some type of shearing. So natural fractures will also start shearing against each other if you start pumping fluid. Okay, and then there will be some microseismicity generated, which can also be modeled. Plus, once this modeling is done, you can start predicting your the oil production or gas production and water production. So you can see this is kind of a sensitivity modeling where you start modeling your production based on what kind the length of the natural fracture and what is the extent of your natural fracture. Okay. All of these things you can change in different simulations and see how much the well is producing. Okay, so this one is 20 meter cube per day, 30 meter cube per day, and so on. So this is the cumulative production and this is the production rate, and this is the actual well. So you can see these types of geomechanical model starts at the beginning of the exploration. I mean, at the beginning of the exploration phase, and you have to do this until the end of your field life. Okay, so geomechanics is there from the beginning to the end of the field. So once you fractured the well, if you start coring the well, you can see that this is one of the places where they obtained core after they fracked the well. So you can see the much of the sand they pumped is within that fracture. You can see here. So it's a probed fracture, high permeability probed fracture. Okay. Then again, you can see that these are different cores from the fractured well. So you can see that the sand is there. So most of the fractures look quite planar to me, like planar. Some of them are stepped, like this one. So a stepped fracture, but most of them are planar fractures. Okay, and some of them have propent, some of them have no propent. Okay, so just because you are pumping the propent does not mean that it's going into the fracture. Okay, sometimes it will go in another direction unexpectedly rather than into the fracture. Okay, so into the intended fracture. You can see there is no propent in this one. Next, so you need to so if you want to do hydraulic fracturing modeling, okay, so you need to first calculate your stresses to put in your simulator. Okay, so if you have no other data, for example, no well logs, nothing else, so this is the most common assumption they do, is that you have the overburden stress, which is the stress of your rock plus fluid above a given point. So that's approximately 1 psi per foot, which is approximately 2.31 gram per cc. So this is the weight of the rock plus fluid above a given point. Okay, that is called the overburden stress. Then we have this hydrostatic stress, or hydrostatic pressure we call it, which is the pressure of the interstitial fluid above your above a given point. Okay, so this is the hydrostatic pressure, which is about 0.433 psi per foot for fresh water, or if it's a brine like salty water, then you can take 0.465 psi per foot. Okay, so pore pressure, lithostatic pressure, and then your fracture gradient, which is the fracture gradient means what? Your once you reach this fluid pressure, then your fracture will start propagating away from the wellbore. So this is generally observed as SH min, okay, minimum horizontal stress. Okay, so it will always be between overburden and pore pressure under normal and strike slip faulting regime. But if it's a reverse faulting regime, then your overburden becomes equal to your fracture gradient. So let's discuss the horizontal stresses. So you know that there are 4 stresses that we calculate generally for hydraulic fracturing modeling. Okay, so one is the overburden stress, one is what? The pore pressure, and then we have the minimum horizontal stress and maximum horizontal stresses. Okay, so where do these come from? So this minimum and maximum horizontal stresses, the difference between them comes because of the plate tectonics. So imagine yourself, if I place you at 1 kilometer depth. Okay, so what kind of pressures will you feel? You will feel the pressure of the fluid on your entire body, that is the pore pressure. Then you will feel a pressure on your head, a weight of the rock above you, rock plus fluid above you, which is your what? SV, vertical stress. And then you will feel different stresses in your front direction and your sideways direction. So those are SH min and SH max. Okay, So you can see those are coming, those different horizontal stresses are mainly coming from plate tectonics, because these plates are rubbing past each other, or they are pulling apart from each other, or they are pushing against each other. So that is where you get the differences in the sideways stresses, which is your SH min and SH max, and they are mostly unequal in most cases. Okay. So one place where they are rubbing past each other is this Juan de Fuca plate in Western California. So there's a lot of earthquakes happening in Los Angeles and San Francisco, those places, because the Juan de Fuca plate is sliding past the North American plate. Okay? Then we have this compressional area where India is bumping into Eurasia. So you have this Himalayas are forming because of that. And so this is one example of what plates compression. Then we have this Mariana Trench, the deepest point on the earth, where the plates are one oceanic plate, Pacific plate is subducting underneath the Philippine plate. Okay. And then you have these places in the mid-Atlantic ridge where the plates are pulling apart from each other. And there is a lot of volcanic activity in these areas. Okay. So new crust is forming. Okay. So Europe and North America, they are moving about 1 inch away from each other every year. Okay. So new crust is forming here. So because of these phenomena, your horizontal stresses are never equal. Okay? They will always be unequal, mostly. And these arrows that you see here, these arrows are the direction of the plate movement. Okay? So you can see in the mid-Atlantic ridge, the plates are moving apart from each other. Okay. Now let's go back into discussing the hydraulic fracturing. So as Madam mentioned before, so first part of the hydraulic fracturing is what? We just pump, everything else is closed. We just pump the fluid, the pad fluid, which is called the pad stage. And then we get the entire length of the hydraulic fracture. Okay. Second stage, we open this sand pipe as well as the this water pipe, and they are mixing together plus some chemicals, and they are being pumped together. And this is called the slurry stage. Okay, SLURRY. Okay. And then if you keep pumping, okay, so there is one confusion here. That is, people think that the entire fracture will be covered by this propent. That is most likely not the case. That is the most ideal case, where you think that the entire fracture will be covered with propent. So here you can see that ideal case here. Okay, so this is the fracture length, this is the fracture height, and this would be called your fracture half length. Okay, from there the well bore up to the end of this fracture. So yeah, so but the ideal case, this is not the ideal case. The ideal this is the ideal case, but the actual case is somewhat like this. You see, this is the big fracture, and the amount of fracture propent covered by the propent is only about this much. Okay? So it will never cover the entire fracture. Okay. So if you want to, in the modern hydraulic fracturing simulators, you need to put all your stresses. So suppose you have well logs, how do you calculate the stresses? Okay? So you have from the well logs, what you have the compressional and sonic slowness. Okay, so slowness means what? It is the microsecond per feet unit. Okay, so if you take the reverse and multiply with this number, so you will get the VP for the P wave slowness and VS from the S wave slowness. So you will get VP VS. Okay, in kilometers per second. Okay, so if you have the log data. Then you have also have the density data from the log. Density is mainly given in gram per centimeter cube. So using this formula, so rho times Vs square blah blah blah. Okay, you get the Young's modulus. Okay, and from this formula you can get the bulk modulus, and from this formula you will get the shear modulus of the rock. This is the Poisson's ratio. And in the Poisson's ratio, you see you don't need any density. You can just use the VP Vs and get the Poisson's ratio. Okay. And we also have this alpha. Alpha is called the Biot coefficient. It is equal to 1 minus K bulk, which is you calculated from there, divided by K grain, which is your grain bulk modulus. How do you get the grain bulk modulus? You can do some lab measurements to get the grain bulk modulus, or you can also find some value. If you know the lithology, you can find that value from the literature. Okay, and you can change it a little bit. Okay, to get your alpha. So these are the parameters that we need to calculate our mechanical properties and stresses. One thing about these Young's modulus, bulk modulus, and shear modulus. If your velocity is in kilometers per second and density is in gram per centimeter cube, you will get these three modulus in gigapascal. Okay. Poisson's ratio has no units, and Biot coefficient also has no units. And your logs are mostly the slownesses are in microseconds per foot. So now that you have calculated your mechanical properties, you have to calculate your stresses. So the overburden stress you already know because you have the density logs. You can just integrate those density logs, or you can assume like 1 psi per foot and calculate your overburden stress. But how do you calculate your pore pressure? As you already know, you can multiply with 0.44, whatever is your depth in feet, you can get the pore pressure if it's a normal pore pressure. If it's overpressure, then it's a different way of calculating it. Okay. And then you have SH min and SH max. So these are the equations for SH min and SH max commonly used. Okay. This part that you see here, up to alpha pp. Okay. So this much. Up to this much. This is the horizontal stress because of the because of the vertical stress. Okay. So this part of the horizontal stress is coming from the vertical stress and the Young's modulus and pore pressure. Okay. So even if you had no tectonic stresses, you would still have these horizontal stresses. Why? Because once you put a vertical stress, your rock will try to expand sideways. Okay. Because of the Poisson's effect. But if it cannot expand sideways because it's in the subsurface, then it will generate some stresses. Okay. So this part is that stress because of the weight of the rock. Now, the second part here, you see, you have the Young's modulus, and then you have these tectonic strains, epsilon H min and epsilon H max. So these are the strains coming from your plate tectonics. Okay. So if you add them to the stress that is caused by the vertical stress, then you get the total SH min, the minimum horizontal stress. Similarly, this is the formula for SH max. So there is slight difference between this and this. Okay, please take a look. Instead of minimum strain, you have the maximum strain here, and instead of maximum strain here, you have minimum. So you have just changed. You have just switched the places here, and you can calculate the SH max. Okay? So suppose there was no plate tectonics going on, then you can just forget this part of the equations. Okay. So in that case, if there is no plate tectonics, your SH min will become equal to SH max because this part here is the same as this part. Okay, so there will be no difference between the SH max and SH min. Okay, so it will be a isotropic stress rock. Okay, in the horizontal direction. Your SV will still be different, but your SH min will become equal to SH max. Okay. And these are mainly calibration parameters. These are not actual strains. Okay. So this is one example. So you see, this is the Young's modulus, Poisson's ratio, and Biot coefficient. Okay, so these are there, and these are the different formations. For example, Kenny shale, Sycamore limestone, Woodford shale, Hunton limestone, Sylvan shale, Viola limestone, and then bromide formation. So this is Young's modulus, Poisson's ratio, Biot coefficient that we calculated using these equations. Okay, and then we applied these equations to get our stresses here. Okay, so these are the two stresses, SH min and SH max, using different types of tectonic strains. You can look at this. Okay. This is the pore pressure, assuming normal pore pressure of 0.44 psi per foot. This is the vertical stress, assuming 1.1 psi per foot. Okay, so this is the vertical stress, and this is the SH max. This is the SH min. Okay, the dotted lines are SH min under different tectonic strains, and this is the SH max. So now you have the full range of data you need to start building your geomechanical model. You have all these stresses. And how did I know that this is the correct calibration? So that is coming from a hard data. Okay, so some people fracked that formation, the Woodford shale. Okay, and from that fracking, they got this minimum horizontal stress. So I changed these tectonic strains here in such a way that these lines are very close to that minimum horizontal stress at this location, okay, because I know the depth at which the fracture happened. So this is called the calibration of stress calibration. Okay, unless you calibrate your stresses, you never know whether your stress model is correct or not. Because if your stresses are way off, then your final hydraulic fracturing geometry will be extremely different from what it should be. Okay, so you need to have a really calibrated model, and the more calibration points you have, the better. But in this case, I had only one calibration point. So these are the equations, the same equations. If you divide those by depth, then you will get the gradient. Okay, SH mean gradient and SH max gradient. And these are called the Blankton and Olson equation. This part was called the Eaton equation, E-A-T-O-N, and then when these were added together, so these guys did it, Blankton and Olson. Okay. So this is your entire stress model. Okay, let's finish here. Okay, next class we will do a calculation. So let's finish it here. So let me ask you some questions. Okay, how would you differentiate between a natural fracture and induced fracture in a core? Please, guys, please start answering the question. Okay, I have just a few questions, and then we will be off from here.
Sir, there would be cement deposition in those natural fractures. So while log we can see those.
Okay, yeah. So cement is the one that's the main differentiator between the two. Correct. Okay. And what type of cement would you see? Like, what is the chemical composition of the cement?
Like calcite, dolomite, and all those.
Yeah, correct. Okay. So please, all of you, try to answer. Okay. And which is brighter in an image log? The high density or low density?
Low density.
Low density will be anything that is low will be darker, and brighter means more. Okay. So higher the density, the brighter, and the lower the density, darker. Okay. Same for resistivity. Higher the resistivity, it will be brighter. Higher the lower the resistivity, darker it will be. Okay. So, okay, in which cases will you get drilling induced tensile fracture that is not along the entire well bore, like along a vertical well bore? So in what case will you not get a straight drilling induced tensile fracture?
So if you use high density mud.
No, I'm asking about the shape of the fracture. Okay. So in which case will you get this type of a straight fracture versus these types of N echelon fractures? Then induced fractures I'm talking about. Okay, drilling induced tensile fracture. So answer is, in a vertical well you will get this type of fractures that go from top to bottom. In a deviated well you will start getting these types of drilling induced tensile fractures. Okay, so that is the answer. Name some of the hydraulic fracturing software. What can you name? Do you remember the names or no?
So Baker Hughes, Joel, and then we have
Yeah.
flat.
Yeah, all of these can do hydraulic fracturing, but these two are mostly geotechnical, and these are mostly used in petroleum. These. Okay. What causes the difference between the minimum and maximum principal stresses or horizontal stresses?
Plate tectonic moment.
Yeah, correct. Okay. Okay, so this is it for today. If you have any questions, please you can ask now.
Sir, I have one question. What is the difference between that sleeve fracture and angle fracture, whether that would be high or low?
So you are talking about these natural fractures?
No, you have shown one slide that contained the different type of fractures. Yes, the
Is this
slip
one?
one. Yes.
So these are all natural fractures. Okay, so these happen during different geologic time. So these types of opening mode fracture mostly happen if you're suppose there is a very high fluid pressure. Okay, so this is parallel to bedding. Okay, so if this is
So I'm
parallel,
asking like the difference between slip fracture and that angle fracture, like low angle or high angle fracture.
okay, that's what I'm saying. Yeah. So these are called different modes, like mode 1 fracture, in which there is opening mode fracture. Okay, and these are called faults. Okay, small faults. So these are mode 2 fractures. So if you want to discuss that, we have to go into depth of some diagrams. I did not put those things. Okay. If you want to know, please, are you from ISM or no?
Yes, sir.
Okay, so please come to my office because it will be I need to pull out a diagram to show you when this will form versus when that will form. Okay? Because you have heard about Moore circle and failure envelopes or no?
Yes, sir. Yes, sir.
Yeah, so we have to explain using Moore circle and the failure envelopes. So,
Okay, sir.
okay, okay. Anybody else?
Okay, thank you, Professor Shanton, for
Oh,
a good lecture
okay, thank you,
and
sir.
excellent outlook on the different types of natural fracture. And participants, if you still have any type of query in later stage, you can be touch. You can get touch with Professor Shanton Ghosh. I think he will be quite helpful to clear all the doubts. And this is the starting of the day, and I am really overwhelmed with your participation. And I will share all these video lectures to all of you so that you can get in your spare time more details about the course. At the same time, it is always suggested you can refer some books that is relevant to this course. And see you tomorrow. Obviously, I just request you to join tomorrow by 9 o'clock. So tomorrow the class will be started positively by 9 o'clock. Okay, positively at 9 o'clock. So thank you all. Have a nice day. So we are closing this the session of the first day. Okay.
Thank you, sir.
Okay. Stop.